Now we'll see one important detail about recursive enumerable languages and its complement. Read this statement. A language is recursively enumerable but not recursive, then its complement is non-recursively enumerable. That means to understand that, first of all, let me explain this picture. We know that these are all finite sets, okay, finite languages. So here these are all regular languages, these are all context free languages, this circle, okay. That means if I write any point here, that is finite, also regular, also context free. That means every finite language is regular and context free, so it's a closedness. Now if I write any point here, this is a language which is recursive but not context free, but not regular, but not finite, okay. Such points are these. Now similarly, this point is nothing but it represents a circle, which is this one. That means recursively enumerable language but not recursive, okay. What about this one? This is recursive but not context free, but recursively enumerable. So all these points are part of this recursively enumerable circle. We know that, right? So whenever you have a total Turing machine, then we'll have a Turing machine. So automatically recursive languages will become recursively enumerable languages. So any language is recursive, automatically recursively enumerable. But there are languages like M halts on W, okay, and where M halts on W, M halts on X. Such language is recursively enumerable but not recursive. Already we proved it. Similarly, membership problem, M accepts X. Forget about that. Now there are some languages, for them there is no Turing machine. That means for some of the languages we can't construct Turing machine. I will give you an example, that is M hash X, where M does not halt on X, okay. M does not halt on X. Sir, why M hash X where M does not halt on X? Why such language is not recursively enumerable? How can you say that? I am going to tell that. We know that M hash X where M halts on X is recursively enumerable, correct? But not recursive. Whenever you have a language which is recursively enumerable but not recursive, then its complement should be definitely either here or here. First of all, let me tell that point. Whenever you have a language which is recursive enumerable but not recursive, its complement, let's denote it by L. This is your language L, and L bar will be definitely either here or here, okay. But L bar cannot be here. Why? Think about it. Because whenever L is here, L bar is here, let's say, then L bar's whole bar is L, correct? You know one thing, whenever a language is recursive, its complement also recursive. Already I proved it. That means if L bar is recursive, L bar whole bar, which is L also should be recursive. But already we know that L is not recursive. Then L bar cannot be recursive. If L bar is recursive, then L has to be recursive. But we know that it is not possible, because initially our assumption itself, a language is recursively enumerable but not recursive. Such kind of languages we are discussing. So whenever your language is here L, its complement cannot be here. So hence here, it cannot be anywhere, because all are recursive languages. So recursive's complement is recursive, but already we know that our language is not recursive. Then its complement should be either here or here. These are the possibilities, first of all. But this possibility also cannot arise. Why, sir? Recall one result already I told you in my lectures, that is whenever a language and its complement are recursively enumerable, recall L and L bar are recursively enumerable, automatically they will become recursive. Okay, so here you are saying that L is recursively enumerable, L bar is also recursively enumerable, then automatically L will become recursive, then L will become recursive, then L will go here. That means L cannot be here. Right, try to understand. If L and L bar are recursively enumerable, the only case is they should be recursive, then they can't be here, because these are all points where they are recursively enumerable but not recursive. So the only possibility, I tried keeping L bar here but that was not possible, I tried keeping L bar here but that was not possible. So now the only possibility, it is one of the language, right? So L complement is a language that cannot be here or anywhere we tried, then it should be here. So that's why from now onwards, whenever you have a recursively enumerable language, its complement should be non-recursively enumerable. Remember it. Now come to this halting problem. So halting problem is recursively enumerable but not recursive. Already I proved it. So m hash x, where m does not halt on x, is complement language. Recall. Example, L is m halting problem. What is halting problem? Halting problem is nothing but collection of strings m hash x where m halts on x. What is L bar? L bar will be again collection of strings such a way that m does not halt on x. Correct? If m halts on x, then that will become this language, right? That's why m does not halt on x will become L bar. Right, in that way easily we can understand. See, what is your language L here? Example, m hash x where m halts on x. Then what is the other set of strings? M hash x where m does not halt on x, right? That's why it will become L bar. So now you know one thing, whenever you have a language L, its L bar should be always non-RE. That's why m does not halt on x will become non-RE. In that way, so we are going to decide some language is non-recursive enumerable or not. Okay, so it's very important. It looks like, no sir, what is the big deal in this one? So this is one of the result. Okay, fine, we understand, but what is the advantage of this one? I will tell you. Example, let's say you have a language L and you know that that is recursively enumerable. You know that, but not recursive. Okay, fine. Then someone asks about sometimes L bar, but you know about L, then you can talk about L bar easily. Understand? Example, see how to answer this kind of questions. Let's say they gave you a recursive language, and they ask what is L bar? Is it recursive? They ask this kind of questions. Is it recursive? Is it recursive enumerable but not recursive? Or is it regular? That kind of question they ask. Then easily we can answer. Example, one of that example I will give you. There is a language L which is recursive. Then what is L bar? We know that whenever a language is recursive, its complement is recursive. In that way we can find out. I will give you one more example. So far we have seen a construction of n. Using that we have decided whether a language is decidable or not, right? Now what we are going to do is, so we are going to understand that process in a clear way and easy way to quickly try these problems. Like, there is a problem. I want to check whether it is recursively enumerable or not. And sometimes I want to check whether it is non-recursively enumerable or not. That kind of questions. So using this method, we can easily check whether a language is RE or non-RE. Let's try that. This process is called reduction. Of course, already I taught you reduction. Whatever you did up to now, did you remember constructing this Turing machine is nothing but a reduction process. Okay. Now we will see this process again by keeping the perception in mind that we are doing reduction. Okay. Let's do that. So example, let's say you have problem called m halts on x. Okay, you want to check whether a given Turing machine m halts on x. So you have this kind of strings. Now we are going to map or reduce these strings to another form. How we will see? What we did is, so we took m and x and we have hardwired them into another program called n or Turing machine. So we ran m on x, correct? If m halts on x, then what I do is, and one more thing, sir, what is this Turing machine n? Already we have discussed, that's why I'm not teaching that, but let me teach. Otherwise, you will get confusion. What is this Turing machine is? This Turing machine takes this problem m and x, and m will be simulated on x. If m halts on x, then it is going to final state. If m does not halt on x, then if it loops, then your Turing machine also looping. Then in that case, that is Turing machine ends functionality. Which, with respect to that, you tell me what is going to happen. Can I say like this? So finally what you did is, whenever you have taken m and x such a way that m halts on x, then automatically your Turing machine n is becoming infinite, correct? Because whenever m halts on x, you are accepting every string. Then I can say that your Turing machine n is infinite. Let's treat this as a new problem. Okay, now this problem is reduced to this problem. M halts on x is nothing but now n is infinite. Now m does not halt on x, then what you did? Then your Turing machine n is accepting a language called finite. So we have now two different set of problems. Let me focus them. What is the first problem? Whenever m halts on x, what is the language which is accepted by n? That is language of n. Language of n is infinite, correct? Remember it. So it is there. Next, if m does not halt on x, then you will be busy looping. Then the Turing machine n won't accept any input. Then what is the language that accepts in that case? That will be finite. Now I would like to focus here very clearly. That is, if m halts on x is a language, right? So what is the language form here? Simple, m hash x, such that m halts on x. Remember it. This is a language form. Collection of all m hash x patterns where m halts on x is also known as halting problem, correct? So here whenever I write m halts on x, that means what? My intention is this one, m hash x where m halts on x. So what is the language form here? N is infinite. So all the Turing machines whose language is infinite, that means you can treat like this. I collect all the Turing machines n, this kind of Turing machines, any kind of Turing machines, so that language of n is infinite. Now you can see two languages here, correct? One language is m hash x where m halts on x. Second language is collection of Turing machines where language of n is infinite. So forget about that language perspective. So directly we'll see, this kind of form. Both are same, of course. So from now onwards, m halts on x can be decided. That means, if you want to know whether a particular Turing machine halts on x, then simply construct this kind of Turing machine. Then if n is infinite, such Turing machine after constructing, if that Turing machine accepts infinite string, then m halts on x, correct? So this is called reduction. Once you have reduction, then we can see lot of important details here. I will tell you. So we'll postpone this one. Let me cancel this one first. Only focus on this part. This is called reduction. So what is the advantage of this reduction? We will see. If m halts on x is reduced to n is infinite, so the meaning I am clearly explaining you, because that is important. So if you learn in high level, in a superficial way, without really understanding the concept, then you do wrong things, okay? That's why I am spending lot of time. Please understand it. So m halts on x means, this has a total Turing machine. Really, then what should happen is, if m halts on x, it should say yes. Here yes no means accept reject, okay? So yes no are easy words for us. M halts on x, it should say yes. M does not halt on x, it should say no. Such total Turing machine is impossible, correct? But now I can construct total Turing machine for this one. How you see? The problem is m and x, right? Using m and x, for which you want to check whether you want to check the halting problem. So take that mx and write a code for n. Then a total Turing machine, n will be created. Take that n and we assume that, let's say, for this n is infinite problem, there is a total Turing machine. That means what? For this language, there is a total Turing machine. That means given a Turing machine, someone can check whether that language of that n is infinite or finite. Okay. Yes means we can say n is infinite. No means n is finite. Such total Turing machine really exists. Then what happens, we'll see. I take m and x, then I create this kind of Turing machine and I give input here. Now if answer I get yes, then I can say that my Turing machine n is infinite. But my Turing machine n is infinite only when m halts on x. So I can say m halts on x. Now if m does not halt on x also I can tell, because really you have a total Turing machine, then given m hash x, we should be able to tell whether when m halts on x, when m does not halt on x. So how I can tell m does not halt on x, I will tell you. So you will be taking mx and you are creating Turing machine n, and that Turing machine will be given to this input, this Turing machine, then n is rejected by this machine. That means n is accepting finite, but n accepts finite only, m does not halt on x. Then that means, so we are going to give no result here. So here finally this kind of total Turing machine can be constructed whenever you have this kind of total Turing machine. Okay, now from now onwards I don't go into this much details, but you should understand, because that is same thing every time. So finally n is infinite is nothing but this problem. That means collection of Turing machines whose language is infinite. That question is that the question doesn't have total Turing machine. So if it has a total Turing machine, then we'll get total Turing machine here, but it is not possible. So finally this language saying whether given a Turing machine is infinite or not, that is a language. This is a language form. What is that? Collection of Turing machines whose language is infinite. So that is dash language, definitely not recursive language. Remember, not recursive. I am not saying exactly whether it is recursively enumerable or not recursively enumerable. I am telling definitely it is not recursive, because if this is recursive, automatically this was becoming recursive. Means what? Total we have a total Turing machine, right? Since there is no total Turing machine, so it is not recursive. So that's why here also, I mean, that will satisfy, correct? If this is recursive, there will be a total Turing machine. Just now I told you, right? Then here also we get total Turing machine. That is impossible. Finally, we'll come to shortcut or summary. Whenever you reduce your m halsa next to this kind of n is infinite, then if this is already what? Let's see. There is no total Turing machine means what? This is already non-recursive, correct? If this is non-recursive, remember, definitely this is also non-recursive. Okay, that is one thing. Second, if it was, let's say, if it is not a recursive, that means if it is not recursively enumerable language, okay, as example, then this is also not recursively enumerable. Why? If it is recursively enumerable, then there will be a Turing machine for this problem, okay. Now see, then we can construct Turing machine here, but I am not discussing that, because I am going to take, because so m halson x is not a, this is not this kind of case, right? Correct. M halson x is recursively enumerable but not recursive, correct? So that's why I don't want to discuss this concept here. I am going to discuss this whatever the logic I told you for another problem, that is m does not halt on x. Let me take the second reduction. What was that? So we had a reduction like this: m does not halt on x. These instances are reduced to what? N is language of, that means n is not infinite, that means finite, correct? Yeah. Now, if m does not halt on x, recall what is that language it is? This language is non-RE, correct? Already we know that, remember it. That means there is no total Turing, sorry, there is no Turing machine at all. Okay, so why there is no Turing machine, sir? Because the language is non-RE. If there is a Turing machine, it is a recursively enumerable language. Since we know that this is not a recursively enumerable language, it cannot have Turing machine, remember it. But you want to claim that there is a Turing machine here. For which problem? Given a Turing machine to check whether it accepts finite or not. Otherwise, this is the clear format. So collection of Turing machines. I want to have a language. What is that language? Collection of Turing machines whose language is finite this time. Correct? Whose language is finite. For that, if there is a Turing machine, how it should work? First of all, we'll see. Okay? Really, there is a Turing machine. If you give a Turing machine code anything like this n, then it is going to accept sometimes. Definitely there should be some accept, maybe reject, correct? This is a general structure of Turing machine. Maybe loop, correct? So usually whenever you have a Turing machine, we represent like this. Now see, you know that there is no Turing machine here, right? But I construct. How, sir? What is your problem? M does not halt on x. Really m does not halt on x, then I should be able to accept m hash x, correct? Such Turing machine I want, right? So whenever m does not halt on x in the input, then we should accept such strings. For that I want a Turing machine, but there is no such Turing machine, but I can construct. How? Take such m and x, create this machine n, now give that n to this language, this Turing machine. Then this Turing machine sometimes accepts, correct? When it accepts, whenever n is finite, it accepts. But we know that whenever n is infinite, the case is definitely m does not halt on x. then automatically we can decide about m does not halt on x. That means decide means we can draw a Turing machine. How you see? Your initial problem was m hash x. Whenever m does not halt on x, we should be able to accept such Turing machine we want. Okay. So I'm not constructing total Turing machine. I'm showing Turing machine. So here I have a friend. Who is that friend? Just now we discussed, right? There is a Turing machine to check whether n is finite or not. So what we do is whenever m hash x is input, then we are going to construct a Turing machine called n. That means we are going to create a code called n, and we know the story of n, correct? This kind of Turing machine. So this kind of Turing machine will be created, that will be given as input to our friend Turing machine, right? That friend Turing machine which we have seen, that is going to sometimes accept some strings. When it accepts, whenever really it accepts anything, then we definitely know that at that time the given input n is finite. But we know that whenever n is finite, the only case is m does not halt on x, then we accept. Finally, whenever m does not halt on x, then definitely n is going to be finite. So this our friend is, we have a Turing machine to check whether n is finite or not. We use it, using that, we will know that, then using that I can create a Turing machine in that way. Sir, I have a doubt. What is that? Because, sir, what if this friend Turing machine is in the loop? Whenever it is in the loop, then definitely the case is n is infinite, maybe, correct? Because whenever this is a Turing machine for n is finite, correct? This is a Turing machine for checking a Turing machine is finite or not. Really your Turing machine is finite, it will eventually accept. If it is in loop means n is not finite, n is infinite. So at that time our Turing machine also will be in loop, no problem, but still Turing machine is Turing machine in that way. So finally we can construct a Turing machine here. I am not saying that I have a total Turing machine. If a wrong input is given, that means if m hash x is given such a way that m halts on x, then I don't need to check tell any answer for that, correct? Remember one thing, any Turing machine's property is, if this Turing machine is for m hash x where m does not halt on x, then if m does not halt on x, it should say yes. If really m halts on x, then it can go to loop, otherwise it can reject the strings, anything it can do. That is a property of Turing machine. So Turing machine should answer only, it should accept, it definitely should accept the strings of that language, but for other strings it can do anything. But total Turing machine's property, when you give a string, if that example, let's say this is a Turing machine for some language L, if you give a string in that language, it should accept. If you give a wrong string, it should reject. Understand? That is total Turing machine. Since here we are constructing ordinary Turing machine, that's duty is very simple. M does not halt on x, then we should be able to detect. That we can detect, correct? So this is about constructions. Sometimes, first understand high level idea so that automatically you can understand the Turing machine constructions. Okay. Now, you have any questions related to this Turing machines, whatever, while reading, watching these lectures, please post the questions into the forum. Okay. Now finally what I want to say is, here your problem was m does not halt on x. Halt on x is reduced to n is finite, correct? And the language form is collection of Turing machines where language of n is finite. Now this is already, this language doesn't have Turing machine, then this language should not have Turing machine. Whenever there is a Turing machine here, I should be able to construct a Turing machine here, correct? Whenever you have a total Turing machine here, I will be able to construct a total Turing machine for here. So that's why what I want to tell you is, here you have definitely no Turing machine, correct? If you have Turing machine here, I can construct, but it is impossible. So definitely there is no total Turing machine here, or sorry, no Turing machine here. So this language, what we are talking about, that is non-recursively enumerable. In that way, from now onwards, we can easily check whether a language is recursively enumerable or not recursively enumerable, correct? Now let me summarize. Whenever you reduce your language to, that means, sorry, if m does not halt x is reduced to your language, then we say that language is not recursively enumerable. If m halves on x is reduced to your, what was the problem? N is infinite, correct? So here in this case, definitely I can say that your language is not recursive. I don't know whether it is RE or not, but definitely not recursive, because if this is recursive, then this also should be recursive, but m halves on x is not recursive. So these two things you remember. Okay, now we'll see one example using whatever the knowledge we have. We try to answer it. Okay, given a Turing machine, whether m accepts epsilon. First of all, don't go for constructions. Think about, whether can we have a Turing machine for it. So what is the question? Given a Turing machine, can we check whether it accepts epsilon or not? For that problem, I can construct a Turing machine. So first I will tell you what is the language form of this one. Here the meaning of this one is collection of strings like m, okay, such a way that m accepts epsilon. This is a language form here, try to understand. Collection of strings where they accept epsilon. Now, if there is a Turing machine, what should be its behavior? One Turing machine is given. If that n accepts epsilon, we should say yes. That means we should accept. If n does not accept epsilon, you may reject. So it is not compulsory to reject. You may go to loop also. But remember one thing, really it is a Turing machine for this problem. Given a Turing machine code as input, if that Turing machine really accepts epsilon, we should accept. Okay, remember it. So yes, how to construct I will tell you. Yes, I think we can construct it. Whatever the Turing machine is given n, then read that into one of the tapes. Already I told you. Then simulate that n on epsilon, because we can generate epsilon. Already we have seen it. Then if n accepts epsilon, then you accept. You go to final state. See, I'm just giving my Turing machine's description, how it looks like. Whatever the input is given, I take into one tape or track, and I will write epsilon into another track. Now I simulate n on epsilon. If n accepts really epsilon, definitely after 5 steps or 10 steps or 20 steps, eventually after some point of time, really it accepts, then this Turing machine will go to its final state. Then I can observe it. Being as a big Turing machine, this is my Turing machine. Since this is my code, then while simulating this n, then I can easily check whether this Turing machine is going to final or not. If this Turing machine goes to final, then I will go to final. Such a way I can plan my Turing machine. So yes, it is possible, right? So finally, this problem has a Turing machine. So I can say this language is recursively enumerable. But recursive or not, whenever a language is recursively enumerable, that also can be recursive also, right? Now maybe regular also, maybe context free also, correct? So that is a question. But we know that this problem is not recursive. Why? See, why it is not recursive? Because we can do like this. We can reduce this problem to m halves on x. What I do is m halves on x, then n accepts epsilon. So this kind of reduction I can do. I will show how to do. Example, I create a Turing machine n. Okay. Now because we have lot of experience, directly I am solving the problem. Then what I do is my Turing machine will take this m, this x, and m is m, and simulates m on x. If really m halves on x, then it will go to accept state. Okay. Accept. That means if m halves on x, I am writing Turing machine n's behavior. M halves on x, then whatever the input is given to w, I accept input w. That's it. Okay. Such Turing machine if you have, okay, which is nothing but n. Ask yourself, what is the behavior of n? What is the language accepted by n? Definitely if m halves on x, then definitely you are accepting whatever the input is given, right? So finally m halves on x, then the language of n is sigma star, you know that. So sigma star contains epsilon, so definitely n accepts epsilon, correct? Recall, if m does not halt on x, if m does not halt on x, then this Turing machine is going to accept nothing, then we are going to n does not accept epsilon, does not accept epsilon. So finally this is called reduction. M halts on x problem is reduced to n accepts epsilon, and m does not halt on x instances are mapped to n does not accept epsilon. If you can do it, then only it is the correct mapping or correct reduction. Once this reduction is done, then what you do is, what is your problem? M accepts epsilon or not, right? This m is nothing but this n here. Okay, so for to avoid the confusion, I use n here. So n accepts epsilon, m halts on x. So if this is recursive, what is your claim? If this is recursive, if really this is recursive, then this also will become recursive, but it is not recursive. So this is not recursive. But already you know that this problem has a Turing machine. That means it is recursively enumerable, but not recursive. This is a way we have to prove the things. Okay, so given a Turing machine, whether n accepts epsilon is recursively enumerable but not recursive. Okay.